Morning. My name is Steve Burke. I'm an applications engineer here at Applied Flow Technology. And today I'm presenting, does your compressor piping network comply with API 618? We're going to be going over compressible transient flow, reciprocating compressors in xStream. We'll be doing a single cylinder compressor example, going over the Pulsation Frequency Analysis module, API 618, a 3-cylinder example in series and parallel, and some key takeaways. So our compressible flow products are AFT Aero for steady state, AFT Aero with the XTS module for pseudo steady state or slow transients. For rapid transients, we have AFT xStream, and for pulsation, we use the AFT xStream PFA module. xStream uses a modified form of the method of characteristics technique that's intended for use with rapid gas transients, including heat transfer effects. You can use xStream to model pipe forces, tank discharge events, turbine trips, valve closures, burst disc relief valves, reciprocating compressors, gas pipelines, and steam blowdown events. How does all of this work? The method of characteristics grid for compressible flow is constructed differently than the one we use for liquids. The liquid MOC grid assumes that wave speed plays a dominant role in comparison to the bulk velocity and is able to generate a solution directly at evenly spaced intervals, as you can see in the bottom left here. But working with gases, it's necessary to interpolate results from points in between stations, and the spacing between stations and the time step size are affected by the current factor, which relates to the maximum Mach number in the system, and to the sonic velocity at the maximum temperature. So that's that plus or minus 2C max delta T that you're seeing here. Modeling compressible transients is more complex than modeling incompressible transients or steady compressible flow. Because the bulk velocities are much higher, there's a potential for sonic choking, which must be modeled. Heat transfer and compression effects must be captured by the model. Simple gas assumptions should be avoided, and the system network effects on pressure waves need to be considered. And the pressure waves change as they travel, and they can combine and dissipate or become sharper, which can ultimately affect forces dramatically. Reciprocating compressors are piston-driven compressors. They're conceptually similar to a piston engine, and we use similar terms like top dead center, bottom dead center, connecting rod length, things like that. They're positive displacement, which means that they have an essentially constant flow rate. And they are a new option introduced in xStream 3, which are selected as a subtype of the positive displacement compressor. In xStream, we can model these as single or double acting. A double acting reciprocating compressor is what you see in this diagram here. That just means that it is also compressing on the crankshaft side of the piston. We can model multiple cylinders as a single junction. If you're doing parallel cylinders, we can do that with an opposed configuration, inline configuration, or V configuration. We can also model each cylinder as a separate junction, which is very useful for multi-stage compressors. And when you're doing this, you'll use the crankshaft phase shift option to control the timing of each cylinder relative to each other. So for our first example, we're going to look at a single cylinder compressor, and it's just going to be moving air from a tank at 1 atmosphere to another tank at 1.6 atmospheres. We'll be operating it at 1500 RPM, and we'll be using 4-inch steel pipes to connect everything. So go ahead and open xStream, and we will drag a tank in here, compressor, some bends going up over an obstacle, and finally this other tank. So for the first tank, set the elevation to 0 feet. We want the pressure at 1 atmosphere. We'll just set the temperature to 72 degrees. So for the reciprocating compressor, you want to choose the positive displacement compressor option. And then under type, there's fixed flow and reciprocating compressor. So we're going to set that to reciprocating compressor. There's single and double acting. In this case, we will set it to single acting. For the operating speed, let's use 1500 RPM. For bore and stroke, we'll just keep it square, 4 inch and 4 inch. The rod length we'll set to 6 inches. We'll set the cylinder clearance to 4 cubic inches as well. And the pressure ratio, we will use 1.728. Where that's coming from, you'll see later. So for the suction crank angle, we will set it right near on top dead center. So we'll set it to 10 degrees. And we'll have it closed near bottom dead center at 170 degrees. Now the discharge crank angle we'll have later so that we can get a little more of that compression captured since we have a pressure ratio of 1.728. So let's set that to 260 degrees and the closing to 350 degrees. And then looking at this graph here, you can see the gas volume over crank angle and the different valve events are shown there as well. And then if we were to set this up as double acting, we would also have to specify a rod diameter here so that that could be subtracted out from the volume on the crank side and crank and clearance down here. And so for double acting, you would see 2 gas volumes for rotation and they're offset from each other by 180 degrees. But we will keep this as single acting for now. All right, and then let's go ahead and set up the pipes. We'll use global pipe edit here. Let's set this to ANSI steel. We'll do 4 inches diameter and set all of these to 3 feet. So go ahead and apply the pipe model here to all of the pipes. Okay, so that's set up. And then these bends here, we can just fix auto rotate. We do the same. This label here. Okay. Now we should choose the gas. We're just going to be using AFT standard air. For pipe sectioning and output, I mentioned that the method of characteristics grid spacing depends on the maximum temperature in the system, which is right here, which we will set to 300 degrees Fahrenheit, and maximum Mach number, which we will just leave at 1 for now. And for simulation duration, let's just set that to 1 second. And then I need to set the curvature ratio here for these bends. Set those to 1. And I'll set this to 1.6 atmospheres. Just call that 72. Okay, so as you can see down here in the bottom right, it's all fully defined. So we can go ahead and hit run. Now the artificial transient resolution you just saw was very quick. This works differently when you have PFA on or off, but it's not able to resolve the pulsation if you're not using PFA. So you'll see that the results will take a moment to stabilize, which is not the case when you're using the PFA artificial transient resolution. However, the artificial transient resolution is more involved and you'll see that it takes longer. Okay, and now we have output. Okay, so we have a caution here. It just says that our max transient Mach number was 0.53, so it was lower than 1, so we should lower that for better accuracy. And it looks like the max temperature we chose was good. And going over to graph results, we will choose the inlet of pipe 2, and that is going to be over here at the discharge of the compressor. And we'll look at the static pressure and the velocity. So you can see that it does take a moment to stabilize when we're not using PFA. This is usually between 0.5 seconds and 1 second of simulation time. You'll also notice there's these little sharp points here where pressure and velocity change suddenly. And the cause of that is just the discharge valve opening. So that is a lossless valve. So there will be a sudden change there. That's normal. However, if the change is too large to the point where it's affecting your force results in the system or your frequency results, one thing that you can do is you can adjust the discharge crank angle if it's causing issues on the discharge side, or the suction crank or the suction valve angles if it's causing issues on the suction side of the system. But in this case, it is all looking okay. Oh, and one thing to note here when we're setting up the compressor is this pressure ratio. This is used as an initial guess. The pressure ratio will also ultimately depend on the cylinder geometry in interaction with the systems for the transient pressure ratio. But if it's imbalanced, it can cause issues. So be aware of that. So our takeaways from this are that it takes half a second to a second of simulation time to stabilize when you're not using PFA. With PFA, this is different because PFA performs the artificial transient resolution differently. There can also be sudden pressure changes when a valve opens, and that's because it's a lossless valve. This is normal, but if those changes are large enough to impact your force results or your pressure frequency results in the system, you may need to adjust the valve timing to be more in line with what you're doing for the compression ratio. And then the specified pressure ratio that you put in the compressor properties just serves the initial guess. The actual pressure ratio depends on the compressor configuration and its interaction with the system. But if there's too much of a mismatch, it'll take more time for those results to stabilize. And you can even see convergence issues if it's a large enough mismatch. Okay, so what is the xStream PFA module? That's our Pulsation Frequency Analysis module. This is a add-on module that you can purchase for AFT xStream that adds new functionalities. So Pulsation Frequency Analysis essentially helps you identify natural frequencies and avoid resonance. In this graph here on the right, you can see in one of the pulses that are resonating, the amplitude is much larger than when it's in part of the system where it is not resonating, shown in blue. So that can increase the vibration and noise in the system significantly. Pressure changes travel at a speed that's a combination of the sonic velocity and the bulk velocity. The pulses can reflect at bends, valves, dead ends, or other boundary conditions in the system. Reflected waves interact with other waves in the system, which is the basis for why systems have natural frequencies. An acoustic input can provoke an acoustic response. Reflected waves that cause constructive interference essentially lead to resonance. And this resonance occurs when the reflected pulse takes the same form as the incoming pulse. So again, think back to constructive interference, destructive interference. And this resonance can amplify vibration and noise several-fold. So within PFA, we have two analysis modes. The first is natural frequency evaluation. This image here is what an AI thinks natural frequencies look like. It's probably incorrect about that. So to evaluate natural frequencies with reciprocating compressors, you will set it to the natural frequency evaluation mode. And you'll need to change the compressor to a fixed flow rate type. And essentially it will ring the system with one sharp pulse. And the natural frequencies that we'll see downstream and upstream of the compressor are usually different, so pay attention to both of those. But you can use those natural frequencies and convert them to RPMs to see what could be problematic operating speeds for your compressor. The other mode is steady state pulsation. Again, this can provide results in the frequency domain, but the key difference here is rather than a single pulse to ring the system, there's steady pulsation. So we can see this sinusoidal flow over here on the right. And this periodic flow can come from a reciprocating compressor. You can set it up using the sinusoidal periodic transients for an assigned flow junction, or you can set it up using custom transients on any other junction you want. But the steady state pulsation mode also allows evaluation with API 618 peak-to-peak pressure limits, which is what we are interested in here. API 618 is the compressor counterpart to API 674, which you may be familiar with from AFT Impulse. It's a useful tool to ensure that your compressor is right for your system and that any pulsation dampening equipment is performing as required. And the consequences of extreme vibration can be costly. So it's really important to get the system designed right ahead of time. Industries that might care about this. API 618 analysis is useful for any industry that uses reciprocating compressors. This would most commonly be gas transport, petroleum, and chemical industries, or it could be compressor manufacturers who are designing compressors for the needs of their clients. And this applies to both lubricated and non-lubricated cylinders. Because the performance of a reciprocating compressor is a combination of system dynamics and compressor design, changing the design of the compressor or the design of the system without any modeling is risky. Careless redesigns may lead to unanticipated vibrations, necessitating mitigation and future redesigns. The portion of API that we're concerned with is the section on analyzing pulsation and vibration control, this section 7.9, which dramatically affects compressor and system reliability and performance. We don't model compliance with every single aspect of API 618, which gets a lot into the compressor design itself. We're only focused on what can be simulated with xStream. The API 618 equation that we're concerned with for xStream is the peak-to-peak pressure level limits at base pulsation frequency and the harmonics of that frequency. But effectively, we do analyze it at every frequency up to the cutoff frequency that you specify. And so this peak-to-peak pressure level, it's a function of the absolute line pressure, the inner diameter, the pulsation frequency, and the speed of sound inside the pipe. So applying API 618 to the single cylinder example that we did before, looks like this. You can see the curve over here. This is the API 618 limit. So it's lower at higher frequencies, which can be more damaging. At low frequencies, you can get away with more pressure. But in this case, the pressure amplitude that we're seeing here exceeds API 618 at 25 Hertz. Additionally, it's hard to see in this graph, but it also exceeds it at 75 Hertz. So the initial design does not pass API 618. So the question is, would a multi-cylinder approach provide better results? So our goal for the next example is to compare a 3-cylinder design in both series, so a multi-stage design, and in parallel. And we want them to have the same bulk flow properties as each other and as the single cylinder example, but different acoustic properties. So we'll be using AFT xStream to look at the transient flow properties and the PFA module to analyze API 618. And we'll see that the bulk properties are the same, but that the parallel configuration will exhibit some high frequency flow behavior. And only one of these configurations will be compliant with API 618. So there's some tweaks that we have to make to the design besides adding more cylinders. So the pressure rises need to be equivalent. So we'll want a pressure ratio of 1.2 for each of the cylinders in series and 1.728 for each parallel cylinder. The latter is the same as the single cylinder. And we want the bulk flows to be equivalent. So we'll have the same suction valve angles, the same cylinder geometry, and the parallel cylinders will operate at 1/3 speed since they have 3 times the swept volume per crankshaft rotation. And then we'll have the same base frequency of 25 Hertz. So the cylinder timing will be evenly spaced. So 120-degree offset between each for the parallel, which will give it the frequency of lowercase n times n. And so lowercase n here is the number of heads. The large n is the speed, so 1500 RPMs over 60. And then for the series, since they're all in phase, that would just be 1500 over 60, and they both work out to be 25 Hertz. There's a few other design considerations here. We want the series cylinders to have an earlier discharge valve opening angle because we've dropped their compression ratios to 1.2. And then for the middle cylinder in the series, we want to have it shifted by 180 degrees so that the first cylinder is having its discharge stroke when the second is having its suction stroke, and same comparing the second and the third. And this just prevents pressure buildup in between the cylinders. And then one thing you've probably noticed about multi-stage compressor design is the bore decreases for each subsequent series cylinders. And the reason for this is so that they have the same amount of compression work. And that helps to control vibration. So if you think back to PDV in physics, that's essentially why we're making it smaller. And so this is just a comparison of the designs in steady state, just to verify that we've chosen the correct pressure ratios. In this case, the new pipes that were added are frictionless, but when we go over to the full transient model in a second, we will keep friction in those. But this just verifies that they should provide the same pressure rise and the same mass flow rate as each other. Okay, so I've set up the model here. So these new pipes in between, they all have a length of 1 foot, diameter of 4 inches. And that's the case down here in the parallel submodel as well. So if we look at this one, the pressure ratio has been dropped to 1.2. And we've changed the discharge crank angle accordingly. Other than that, this one is still the same as the single cylinder. And then here you'll see this line shows the phase shift of 180 degrees. And then the bore here has been dropped to 3.651 inches. Other than that, it is the same as the first cylinder in series. Looking at the third cylinder in series, there's no crankshaft phase shift, but the bore has been reduced to 3.33 inches. Going down to the parallel submodel, we can see here that the bore, stroke, rod length, all of the cylinder geometry is the same as the single cylinder model, but the operating speed has been reduced to 500 RPM, and we are keeping the same pressure ratio and the same valve timing as were used in the single cylinder. Looking at the next cylinder, the only difference here is we have this crankshaft phase shift of 120 degrees, and we show that on the graph as well. And looking at the last one, it has a crankshaft phase shift of 240 degrees, which we see here as well. And then looking in analysis setup, the frequency analysis mode has been set to steady state pulsation. And this panel will only appear if you have the PFA module active. We do have the artificial pulsation resolution turned on, which again works a little differently than the artificial transient resolution when you're not using PFA. We've set the cutoff frequency to 150 Hertz. You want this to be 6 times your base frequency. And for the pulsation source, because we're modeling each cylinder separately, you want to choose the user-defined option. If we were modeling them as a single compressor junction, you could just choose the compressor from this list. And because they're separate, we need to specify the speed and number of heads. It's assuming for the number of heads here that they're evenly spaced like the parallel model. So we're essentially using 3 heads and 500 RPM as seen in the parallel, but it's the same base pulsation frequency in the series model. And then I have already run this, and we can see some warnings here. So I mentioned that the grid sizing depends on the maximum temperature and the maximum Mach number. And so we're far enough away from both of those that we're getting warnings. So if this was a real system, you would want to refine those numbers and run it again for higher accuracy. And then looking at results, this is the integrated mass flow leaving the compressors, and you can see that they're roughly parallel with each other. So we have succeeded at having the same bulk flow results. And then looking at the velocity and pressure, you can see from the sinusoids here that we do have the same base pulsation frequency. One thing you'll notice looking at the velocities is there's this high frequency behavior in flows that's visible in the parallel model that is not there in the series model. But the series model has much higher pressure amplitude overall compared to the parallel model. And both of these graphs are taken here exiting the manifold. So at the inlet of pipe 15 and pipe 4, here and here. Then the next graph will be looking at the pressures right at the discharges of the parallel cylinders at these locations. So again, you can see there's that sudden pressure spike when the valves open, and you can see that each cylinder is opening at 120-degree offset to each other, but that together they're forming very much the same sort of pressure pattern as seen in series, just with less amplitude. And there's more of that high frequency pressure oscillation visible here. So you would want to evaluate API 618 at every point in the system. For the sake of comparison, we are just going to choose at this bend here, going into pipe 16 and pipe 15. And we can see that the higher frequency behavior in the parallel model does not prevent it from passing API 618. However, the low frequency oscillations at 25 Hertz for the series model does. It's violating API 618, which we can see graphically here. And then also in the output and pulsation summary, we can see the same thing for the 10 most severe locations for API 618 violations. So both of the systems showed the matching bulk flow and matching base pulsation, which we expected. There was some high frequency flow behavior specific to the parallel submodel, but its impact on passing API 618 was minimal. However, the series design had significant pulsation at the 25 Hertz base pulsation frequency, that prevented it from achieving the API 618 compliance. So that one has failed our API 618 check. So our key takeaways are that due to their pulsation, reciprocating compressors are inherently transient in nature. Number two, this pulsation can resonate with natural frequencies that exist upstream or downstream of the compressor. Third, the compressors with cylinders in parallel can be modeled as a single junction. You can model cylinders separately to represent multi-stage compressors or to capture manifold effects, which can affect your frequency results. Number four, even compressors that appear equivalent in terms of their base pulsation frequency or steady state flow can still have dramatically different acoustic and vibration performance. And because of this, for good compressor and system design, we always recommend modeling the interactions between a system and a compressor using API 618, and you'll need to do this whenever you are adding something to the system, as new components in the system can ultimately change that natural frequency and change the interactions with the compressor. Thank you all so much for joining. If you enjoyed this webinar, we have other resources for you on our website, so be sure to go check those out. We also offer a range of consulting services if you're in need. And we also have extensive documentation and support resources to help you use our software more effectively. And if you have any questions or you're interested in a personal demonstration, please feel free to reach out to us. And thank you all again for joining.